Hello and welcome to our session on adversarial attacks and defense mechanisms. Did you know that a study by MIT showed that well-designed adversarial examples can trick state-of-the-art AI systems up to 95% of the time if no defense are in place? And that's huge. Today we'll explore how attackers can target AI models in image recognition, text generation, and voice synthesis, focusing on techniques like the fast gradient sign method and projected gradient descent. By the end, you'll understand the basics of these attacks and how they exploit AI vulnerabilities to produce misclassifications or misleading outputs. Let's get started. An adversarial attack occurs when an attacker introduces slight modifications to an input, like an image, text prompt, or audio clip, so subtle that humans barely notice them. However, these modifications can fool an AI model into producing incorrect or bizarre outcomes. For an example, imagine a stop sign with tiny stickers placed in strategic spots. A self-driving car's AI might read it as a speed limit sign, leading to dangerous behavior. Core idea is the AI sees small changes in pixel values, word embeddings, or sound frequencies as major cues, leading to misclassification or misinterpretation. In image recognition, attackers often add imperceptible noise to an image. The image might look identical to us, but the model's mathematical interpretation changes. Examples include subtle pixel modifications, slightly changing pixel values in strategic locations, or sticker or path attacks, placing a physical patch on an object in the real world. According to a paper from ICLR, adding just a 1% noise pattern can mislead some neural networks over 80% of the time if carefully crafted. This shows how vulnerable unprotected image classifiers can be. Text generation. In text generation, adversarial attacks involve tweaking input prompts, inserting hidden tokens, or rearranging text slightly so the AI model produces biased or inappropriate responses, excessively long or repetitive text, and leakage of private training data if prompts are crafted to force the model to reveal hidden tokens or training info. For an example, an attacker might add invisible Unicode characters in a prompt, causing a language model to produce strange or disallowed content. So text-based AI can also be tricked if it's not prepared to handle these subtle input manipulations. And next is voice synthesis or speech recognition systems can be fooled if attackers inject near inaudible frequencies or manipulate waveforms. Hidden commands, placing ultrasonic commands in a voice assistant's audio feed so it executes actions without the user realizing, or misclassification. Slight shifts in pitch or timing might push the AI to misunderstand words. A study by Berkeley AI Research demonstrates dolphin attacks using ultrasonic frequencies beyond human hearing to control voice assistants. This indicates even voice-based systems have exploitable vulnerabilities. So, some of the methods that we are going to talk about, or the techniques, starting with fast gradient sign method, is one of the earliest and simplest methods for generating adversarial examples. And here is the step-by-step. Calculate gradient. The attacker computes the gradient of the loss function with respect to the input. Step 2. Sign of the gradient. They take the sign, positive or negative, of that gradient, indicating which direction changes will increase the model's error. And number 3. Scale and add. They multiply by a small factor and add it to the original input. This creates an adversarial image, text, or audio snippet that looks almost identical to the original but confuses the model. For example, if a epsilon is small, the changes are so minimal that humans won't detect them. Yet the model's prediction can flip from cat to dog, and that's the power of FGSM. Second is projected gradient descent, PGD. Is like a more advanced version of FGSM, and instead of doing one gradient step, you do multiple. Step 1 is iterative attacks. PGD applies small FGSM like steps repeatedly, refining the adversarial input with each iteration. Step 2, projection. After each step, the input is projected back to the allowed range of perturbations, ensuring the changes stay within bounds, like keeping them under a certain epsilon. Result, this repeated process often yields stronger adversarial examples, harder to detect, and more effective at fooling models. Many researchers consider PGD a universal first-order adversary, meaning if a model can withstand PGD, it's usually robust against a wide range of similar attacks, though not invincible. Let's walk through a quick scenario. Suppose we have a clear photo of a panda, classified correctly by the model. That's the original image. We compute how the model's error changes if we tweak each pixel. And then we get a sign, positive or negative, plus or minus for each pixel. And we multiply each sign by a small value, say 0.007. That's epsilon scaling. And then we add that to the original. Overlay that scaled noise onto the panda image, creating an imperceptibly different photo. Result, the model now thinks it's a gibbon or something entirely different, even though we as humans still see a panda. This example famously comes from a Goodfellow et al. Paper on adversarial perturbations. It shows how little changes can fool big AI. So, why does it matter? Let's talk about some security implications and mitigations. Image recognition in self-driving cars might misread traffic signs. Text generation in chatbots or AI assistants might output harmful or misleading info. Or voice synthesis systems could carry out unauthorized commands. And potential defenses might include adversarial training. Train your model on adversarial examples so it learns to spot them. Input sanitization, pre-process or denoise inputs to remove suspicious perturbations. Model ensembling, using multiple models can reduce the chance that a single perturbation fools them all. And robust architecture choices, some specialized network designs are inherently more resistant. No single defense is perfect, but combining them can significantly reduce the risks. As we conclude, adversarial attacks exploit small, often invisible changes to fool AI models in images, text, and audio. FGSM and PGD are two core methods. FGSM for quick single-step attacks and PGD for a more iterative, powerful approach. Practical impacts from messing up self-driving cars to tracking voice assistants. These attacks pose real threat. Defense techniques like adversarial training and robust architecture can mitigate, but not always eliminate the threat. A survey by Microsoft found that 25% of companies implementing deep learning were unaware of adversarial threats, indicating a significant gap in defensive measures. We can do better by staying informed and proactive.